Okay, we are back with regression. Remember, just replace the word regression with relationship, and it's easier to understand. There's some typing involved, so I'm going to try to type it where you can see it on the screen. I have my webcam taped to a candle. I'm not sure this will work. So here we go. All right, so if we go back to the data that the professor gave us, the example he gave us for week 13, multiple regression. So again, we're dealing with relationships between variables. In this sense, we're dealing with more than one independent variable. Basically, we run multiple regression to get a better idea of how multiple independent variables affect the dependent variable, because life's not in a vacuum. You have more than one thing. Like, for example, overtime hours. Well, you could hate your job, you could hate your boss, you could hate your coworker. It might not just be performance related pay that's affecting your amount of overtime hours. So we're taking all of these three variables into account right here. PRP, age of the employee, and enjoyment level. This looks like it's on a Likert scale. Yes, it is, measured using a 5-point Likert scale. Okay, so the most tedious part of this is you have to standardize your variables. And the reason we do that is because, for example, we know that in basketball, the highest point value per play you can get is 3. You can have a 3-point shot. That's one play. That's the highest point value in one play you can get. In football, we know that the highest point value per play we can get is 6 points for a touchdown. Okay, I'm not talking about the 1-point field goal or anything like that. Just one play and the max amount of points you can get. Now we know that 3 points is a lot for basketball, 6 points is a lot for football, but how do you really compare them? Because they're not measured, they're the same, they're not the same amount. Two different sports. So we standardize variables when they're measured using different units. As in the case of the PRP is a percentage, age is an absolute number, and then enjoyment is on a Likert scale. So how do you really compare that 1% of PRP is equal to 38 years of age, which is equal to a 3 of enjoyment on a Likert scale? You can't, unless you standardize them. And the only way you standardize them is you standardize them using their own information. In this case, what you do is you would take the number. First, you would calculate the mean of all your data in a column. Then you take the number minus the mean divided by the standard deviation. You don't have to calculate the mean and the standard deviation. I'll show you how to do that. But it gives us a way of comparing variables that aren't measured the same. Okay, comparing the 3-point shot versus a 6-point touchdown. Okay, how do we do that? Pretty simply. The first thing you have to do is let me just check my webcam. Okay, I'm pointed in the right direction. The first thing you have to do is determine what your mean is. So your best bet is to create 2 columns there, okay? And what you do is equal sign, put AV, double click average. I hope you can see average there. Oh, okay, it's going to come up with a parenthesis. You're going to highlight, so you're doing the average of PRP, right? Or let's do the average of overtime. Highlight everything, close parenthesis, equal sign, and there's your average or your mean. Your standard deviation is equal sign, STD, STDev, standard deviation, okay. Highlight again, close parenthesis, and it gives us 3.44. So this is what I did in class, this is what I did just now, the numbers match, okay? And you can do that for everything across the board. And it's the same. Okay, you just pull it across and you got everything you need. Alright. Okay. You see how I did that? I just pulled my formulas across and it matches my same numbers. This is what I did in class. Okay. Now, you have to standardize your data. Now that you know your mean and your standard deviation, you have to standardize everything. Your dependent variable, your 3 independent variables. The way we do that is pretty simple. So I'm just going to show you real quick how to do it with overtime. Check my webcam. Yeah, I think it's okay. Okay. Properly label it. I like to put the name of the variable and then put ST so I know it's the standardized version. The way you do this is you do equal sign, parenthesis, click on that, minus the mean. So you see I just clicked on the box, or you can enter the number, whatever works. Parenthesis, slash, click on standard deviation, hit enter, and boom. Now the thing is, you can't really pull this down because you have to tell the computer where you're pulling your information from, and since it's not side by side, you literally have to go one by one by one by one by one and do your standard deviation. After you've done that for all of your variables, now you have the information to do an unstandardized coefficient or regression and a standardized regression. Okay, you know that you did your standardization correct when you pull over the formula for mean and standard deviation. Okay, I can't explain to you why it's this way. I can explain standard deviation being 1, which makes sense because you've already pretty much factored in the standard deviation, so you really only divided it against itself, so standard deviation is always going to be 1. I can't tell you why mean is 0. I have no idea. But when you get these numbers, you see now you've taken 4 different variables that are measured differently with different means, different standard deviations, and now that you've standardized them, they all measure out the same. Zeros and ones, which tells you you did your standardization formula correct. Okay. Once you've done that, you're going to run a regression. It's the same regression we did with bivariate regression. The only difference this time is what you're highlighting. So let's go back to data. Data analysis. We're going to find regression. Hit OK. You're inputting your Y range. So I'm gonna do it for standardization just because it's easier. Our Y range are our dependent variables over time. Our X range is going to be these 3 variables. Okay. Always check your labels. Always check your confidence interval. Output range. Let's go down here. Hit OK. Now, what I would suggest you do is right off the bat, you need to label if it's standardized. Okay, so you can tell the difference between your standardized and your unstandardized. And do your same thing. Fix all your numbers. Get them down to 2 decimal points. If you have anything that says E, you know it's an exponent, go ahead and fix that. So basically, once you've done the regression for both your standardized and your unstandardized data, and I'll explain why we do that in a second. Why this entire row. Okay, there we go. All right. So let's look at our unstandardized data. Make sure you can see it. Let me go back to here. Yes, you can see it. Okay. All right, we're at our unstandardized data. Okay, now you have to take into account R square, which remember is our percentage of overlap between the dependent and the independent variable. Okay, but now you also have to take into account adjusted R square. And the reason we look at both of these numbers together is because, again, R square has to do with, if you read it, it's a measure of model fit. Okay, remember our Venn diagram where everything's sitting on top of each other? All right, okay, a variation, so this represents the amount of variation in the dependent variable that can be explained by knowing the three variables that we're looking at, PRP, age, and enjoyment. Adjusted R-square lets us know it's a good model fit because if adjusted R-square is substantially different from R-square or our overlap, we then know that some of the change we're seeing in our dependent variable, our amount of overtime, is caused by something else that we haven't taken into account. In this case, if adjusted R-square is significant, if the percentage is significantly different from R-square, then we know that we haven't actually taken into account other variables that are affecting overtime. Yes, we've accounted for PRP, age, and enjoyment, but maybe it could be we hate our coworker and we haven't included that as a control variable, and as a result we're seeing a different adjusted R-square. Okay, that is called junk in the model. It's over here. I wrote it down. If these match, we know that there's not a lot of redundant variables. Sometimes you can measure enjoyment in two different ways, and that might be a redundant variable. But long story short, you want these two numbers to be very close to each other. Okay. Same deal. We are going to highlight our coefficients, look at our t-statistics, look at our p-values. Right off the bat, our p-values tell us that there's a large chance, there's a 42% chance that the change in overtime that we're seeing is related to enjoyment is random. It's not actually because there's not a good causal relationship between these two because we have such a high p-value. Okay. On the other hand, we have age, which is a 0.07, and while it's higher than 0.05, it would be significant at 0.10. And the reason for that is because we're using a very small sample. Remember, we're using 15 employees. That's not a very big sample. So again, we're not even going to really look at enjoyment. We need to include it in our formula. Remember, y, our dependent variable overtime, is equal to the intercept, which is already calculated for us. The computer does it. And then you have to look at your change. Okay. And the way you read this is for every year, for example, for every year in which age increases, the overtime goes down by 0.09. Okay. So you're going to reference your independent variable, then your dependent variable, and how it's affected by the independent variable. Okay. Reading the coefficients, we've already gone through this. Right off the bat, we have a negative relationship. It's a weak negative relationship. You could put a caveat here because of the sample size. You would accept the 0.07, but it's still more than the 0.05. The percentage of performance-related pay and its effect on overtime, again, you would read for every percentage increase of performance-related pay, overtime goes up by 0.58. Okay, so we know that this is a positive, moderate relationship. Okay, basically, once you do your standard variables, you're going to do the exact same thing. You're going to run a regression table. And your numbers really won't change. You see here, R-squared for the standardized is the same. Adjusted R-square is the same, so good. We have a good model fit. Our p-values are not going to change because remember, p-values have a lot to do with our sample size. Since our sample size did not change even with the standardized variables, that's going to remain the same. But the coefficients change because now you're measuring everything the same. Everything is being measured exactly the same. And now you get a more precise idea of how much overlap and basically how much variation is caused by PRP, by age, by enjoyment. Okay, so the way you would word this, however, is different. So for example, because now it's all standardized, you would say for every one standardized increase in PRP, there was 0.72 standardized increase in overtime. Okay, you have to put the word standardized because you're using standardized you're using standardized information. You cannot run a scatter plot for this because there's no way to do a three-dimensional scatter plot using Excel. You can only use the scatter plot in bivariate regression, but it's pretty much the exact same thing. It's no different than what we were already doing. You can do a scatter plot if you really wanted to look at each variable's interaction with the dependent variable, but again, it's not necessary. And again, once you standardize everything, again, you want your zeros and your ones, and that tells that you've done everything correctly. Because now they're all being measured the same as opposed to all these different measures here. Hopefully that explains it. Call me if it doesn't. And that is, I'm clicking around, I'm sorry. That is multivariate regression.